like in India, like we are just 5-6 guys. Then Sadiq was there who moved to Singapore.
Got it.
As a solution architect.
Got it. When did you left?
I left in 2015 March.
2015.
It's pretty long.
Oh,
Pretty long.
way before I joined the company. Yeah, I joined the company in 2018.
Okay.
Yeah. I'm there for a while now. Yeah.
Nice.
And you're working for now?
Right now I'm working for VDX.
I'm sorry.
Oh,
yeah, exactly.
Anything of VDX?
Oh, VDX. Okay. Cool. You're doing the same thing now? Virtualization as well?
Yeah, mostly like virtualization, cloud, automation, and stuff. Prior to that, I was working with Avaya. I was there for 7 years.
I never heard about other customers using Avaya. They were like pretty famous in the past. You know, I had a bunch of customers using. Previously to Red Hat, I worked for Dell. When I worked for Dell, there were like many of our customers using Avaya, especially for conference, right?
So teleconference.
Exactly.
And I was manager of solution architect there for the data centers. In between, like we are using RHOSP, but between like RHOSP version 10 to 12, then it was too buggy. Like I myself filed more than like 25-26 RFP plus bugs.
Got it.
Then we stopped it completely and moved to
it's
stopped
OSP
OSP completely. And
Wanna
this was
switch?
purely
Yep.
VMware data centers.
Okay, got it.
Partner with VMware because they modify the hypervisor kernel, put it on bare metal, and then run fault and go to run the
Okay, got it. So are you still working with VMware?
Yeah.
You can plug it in if you want.
But on my current
No, it's
company,
fine.
primarily like OpenStack.
No,
OpenStack,
I'm good.
okay.
I'm
Yes.
good.
I do all design, deployment
Yeah,
stuff
I
on
know.
Okay.
OpenStack.
Yeah.
I had my
This
talk
one,
yesterday.
this one.
Really? Like, I thought so.
It's
Cool.
the special.
So,
Mostly
Mostly I use like Nova survey kind of stuff.
Got it.
It's an AgTech company.
Although I do have a converter.
So throughput is like
Oh, nice.
everything for them.
But
Yeah,
no,
when I
I
joined
have
Red
it
Hat,
fully
I joined
charged.
primarily to work with OpenStack.
It's
But
new
then,
enough that.
Some
it
folks
is
from my team, they
well.
migrated to another position, and then I needed to take over these accounts.
Uh,
So I ended up like working with
yeah.
everything.
Okay.
Yeah,
So
Good
good.
then, okay.
exactly.
I was in that one.
Yeah, we worked together, right? Cars and the tens are like this.
Cool. Thank you.
Thank you, man.
This one has 6 minutes.
Yeah. We're good.
Do you want the chair? Or you're good?
No, as long as I'm walking, I'm fine.
Okay. I'll just take my stuff off. Just in case.
Yeah, just in case. I'll use my cane. That'll help. I know, it's always hard to be the second to last.
Yeah.
There's only one worse. The last.
The last.
Which Ildiko and I experienced in Sydney.
Yes. It was a very big, very empty room.
Actually, post lunch, like people are with a different mindset.
Yeah,
Last day.
they booked us into a 200-person amphitheater and 10 people showed up.
Yeah, if that, yeah.
It was bad.
Yeah, and everyone was tired, ready to go home or just
Yep.
grab a drink. Yeah. But thank you all for being here. We will start in 4 minutes.
Oh, okay. I didn't know that. Yeah, I can see we have the clock.
Yeah, and it's actually accurate. I think there was one other room where it was like.
Because Chabelle was not.
Yeah,
that was
I
wrong.
think it was ahead. Yeah,
Yeah.
like a few minutes off. It was a few minutes off.
Well, Jonathan was running the time. So.
Oh yeah, how did your panel go?
It was good. Yeah.
It was today, right?
Yeah.
Was it
2:45.
Nice.
Yep. We actually had some questions from the audience.
Oh, there you
I
go.
like that.
It's always nice. to
That's
have.
always an indication the audience is actually listening.
Yeah. I had all that sugar. Let's see. Oh, anyway.
Just as long as I don't eat another hamburger for dinner.
We're going to do a text next week or something.
Oh, it's probably over near the hotel.
No, I think we need to take the train somewhere.
Oh. Yeah, near the hotel, there's 3 American-style restaurants, all in a row, for some reason.
I know, I was there on Friday. Had a dinner there.
Wait, I don't want to come to France and eat.
I mean, you know, for someone who's local and doesn't go to Texas to have that, that's really cool, but I don't know why we are doing it.
Yes. Their idea of mac and cheese was not mac and cheese.
I don't know, I mean, I might have also misunderstood. It could be something else. At this point, I'm a little bit.
Well, they had a big V, vegan, and it showed up with bacon on top. I'm like, what do you not get about vegan?
Maybe it was vegan bacon. These days.
It wasn't vegan bacon, I assure you.
The real deal?
It was the real
That's
deal.
funny.
Well, that's okay. Topher ordered a hamburger, and he ordered the one that was cheesy, but he can't read French, which I can. And so it shows up with a giant slab of brie on it,
Oh,
which he doesn't like.
Oh.
So we ended up trading.
Oh. It's so good.
He was like, I didn't know it had brie on it. I was like, it was on the list of ingredients. But the bacon was not in the list of ingredients for the mac and cheese.
I think the chef just tried to be creative that day.
I guess.
Let's spice this up a little bit. Let's make it more interesting.
So hopefully we'll wake everybody up. I know it's.
Only 25 more seconds.
We can start.
No, we will be on time.
Okay.
If we waited this long, what's another 12 seconds?
That's true.
We are not gonna say anything.
Okay.
Now we can start. Well, welcome everyone. Thank you for coming and joining us for this short little adventure into Edge AI land, which we will talk about today. But when it comes to AI, we will actually talk a little bit more about data than any other aspects of AI, because it's one of the most important but still somewhat hidden components to making all this work. And beyond looking into data, we will also look into what it might take to make AI applications work on the edge, where we already know there are a lot of challenges. But before we do all that, just a little quick introduction to ourselves and the OpenInfra Edge Computing Group, who we are representing here today. And since I'm already speaking, my name is Ildiko Vancha. I work at the Open Infrastructure Foundation as Director of Community, so I do a lot of community management kind of things these days. Community Manager for the Starling X Distributed Cloud project and the Kata Container Secure Runtime project that we are supporting. And I've been with the OpenInfra Edge Computing Group since its inception in 2017, along with Beth.
That's right. So I am a current and former employee of Verizon, or rather former and then current. And I've been involved in edge computing since I had launched a product called Virtual Network Services, which was the first virtualized edge routing solution. And that was back in 2017, amazingly enough. And so I've been sticking with the Open Edge, the OpenInfra Edge working group for all that time. We've published a number of white papers, including this one. I'm also the chair of the Anakit infrastructure project for the LF networking group, so I keep pretty busy. And now a contractor, now that I officially retired, for Verizon as a product manager. So I'm working on some very interesting projects, including AI Connect, which is a product that supposedly connects AI workloads to networks. So there you go. So
that's who we are in a nutshell. And the OpenInfra Edge Computing Group was created in 2017, as Beth already hinted at that date. And what our group was setting out to do, we were exploring what edge computing really is in the infrastructure space. So what components you need and what you have access to on the edge, whatever the edge is, because I don't think that in the past 8 years edge computing and edge definitions really landed in our landscape. So they're still sort of very contextual. In our context, we always focused on the software infrastructure layer and peeked a little bit into hardware just to have an idea of what those software components are constrained to run on. And our white papers we're focusing on use cases and kind of reference architectures and implementations of those in these geographically distributed systems, and we were looking into different architecture models that you would deploy these systems in, and found two main patterns, one being centralized control plane, where you have most of the logic in a central place and edge sites attached, or the other one was the distributed, decentralized model, where you had a lot of autonomy at the edge and they all had their ups and downs, and we will talk about a version of these later in this presentation. And since those initial white papers, now, like everybody else, we are stumbling on the AI space because AI is very interesting, intriguing, and somewhat challenging to make work, especially at the edge. So, edge, what is it? We don't really have one ubiquitous definition of edge computing. What we are calling edge computing is really taking the resources, hardware and software, where the end user is, and making sure that the workloads closer to the end user are able to run, because like how people are holding their phones, which are mini computers, they are great examples of a small device that runs a lot of workloads. And we also came up with another term called cloud edge computing, where you would explore how cloud expands into a geographically distributed system. So taking the cloud concepts and resources out to the edge and build these spider web or different graph style deployments in environments of various sizes. And then all this is influenced through artificial intelligence, which it's also, I think, still kind of being defined in a way what it really is. I think there are some kind of varying opinions about it, so we don't really want to go into deciding which definition we want to believe in. But AI is something that is, on one hand, very resource hungry and intensive, and on the other hand has a lot of demands in terms of data that I already mentioned. And then you need to put a very demanding workload and a very constrained environment like the edge together, and trying to see where that all leads us. So, data. And when it comes to data, I think a lot of people think about the data pools and data sets, and think about the biases that data can bring into AI and all the a little more philosophical layers of it, but we will kind of look at data like if it was part of the infrastructure, and Beth will take you through the details of that.
So it is all about the data, because you can't have AI without data. What influences how the data is partly, there's different types of data. I know there's been a lot of talk about AI in, I've gone to a number of sessions. I don't think anybody has mentioned other than, oh, there's a large amount of it. They haven't really gotten into what that really means, because it's very important when you're doing edge use cases to understand what types of data you're looking at. So there's highly structured data. So telco data is highly structured, right? You know exactly what's in all those packets. So, you know, IP packets, TCP packets, you know exactly what's in them. So that's an example of highly structured data. Unstructured data would be images, and you know that AI is pretty bad at it. Unstructured data, you know, particularly, you know, it hallucinates all over the place. You know, you get the six-fingered monstrosities, you know, because you know, it's stupid. Let's be honest. And then there's things in between, which is semi-structured data. And you see these in all of the edge use cases, all these different types of data. Then, of course, what's important to understand is where that data is being generated. So we're going to be concentrating on the remotely generated data, so AI, so IoT, drones, use cases, augmented reality. We have a bunch of use cases that we'll go into in more detail. But a lot of this data is remotely generated it can be highly distributed. Most of the LLMs that are being used today are mostly centrally generated. It's all being processed in, you know, giant clouds in data centers. So this is a very different kind of use case. The other thing to think about is just how much there is. So data volume. So in an IoT distributed situation, you might have a tiny amount being generated from each IoT device, but there could be 1 million of them out there. Or it could be, like if it's a camera, it's generating enormous amounts of data, but you could have, you know, 50 cameras at a factory site generating enormous amounts of data. What's important about this in terms of the edge is typically many edge are constrained by their networks. And I'll use an example of oil and gas. Where are oil fields? In the middle of the, you know, Gulf of Mexico, or, you know, in the middle of nowhere. And, you know, what type of network are you relying on? Frequently it's satellite, which, you know, is expensive and constrained. And they can generate enormous amounts of data volume. The other thing to think about is, and this ties into data sovereignty, you know, how long is the data useful for? It can be as short as just a couple seconds, or it could be, you know, you have to keep it forever. And, you know, storage at the edge can be a significant problem and a significant cost. So I'm talking about this, right? So what we did in the white paper is we really dive into all the different components that go into the edge infrastructure. So at the heart, of course, you know, we all forget about this being an open stack, right? There's hardware out there. Hardware it's often particularly in IoT environments, or I did an installation in grain silos. These are environments that need to be very highly ruggedized. You wouldn't think grain silos would be a place that they put computers, but they do actually. They keep track of how much grain is in the silo and when it's coming in and going out. So, you know, you have to really think about being ruggedized and lightweight and energy efficient, because again, there isn't necessarily a bunch of energy out in a grain silo. Network, of course, I've already mentioned, which is often constrained because it's in the middle of nowhere. It can be frequently just be down to satellite. Software, of course, you know, you need to keep track of that, and you need to automate it, because every time you send a truck out to touch the installation, that's highly expensive. So you want to minimize the amount of time that you are touching it. And so you want software that can be automatically updated, automatically decentralized, self-managing, because it's not necessarily always on the network. So you want it to be able to sustain its functionality while it's off network. And security. again, these are in areas that are often not monitored, it's not a data center. The other example is, where are the 5G antennas? They're sitting on, if you look around, once you know where they are, you'll see them all over the place. They're on telephone poles frequently. They're accessible. So security cannot be an afterthought. You really need to think that these are physically accessible devices, which means that makes that much easier for data to be stolen from them. And also sabotaged as well. So these are all, in sovereignty, regulatory, geolocation considerations also. So this is a eye chart. I'm sorry. In the paper, it's a little easier to read. So this kind of puts all the components together. And that, as you can see, there's quite a bit of components that need to be put together. So this is like a mini data center in a box, if you will. So you're on for these two, right?
Yes, I think so. So I mentioned already that we explored the infrastructure and architecture space from the perspective of how you're operating a distributed system that is often kind of having this layered architecture, or like imagine it as an onion and you just peel off the layers to get to the core. So when it comes to the centralized cloud, I mentioned that the heart of it really is to have the control functions running in the central cloud. And when it comes to things like AI type of use cases, and you think about the large amount of data that gets generated and also the large amount of data that needs to be processed, and you think about where things are happening in this layered architecture, you really need to also think about the cost, where you're putting what type of hardware, what is available to you to make the system work. And you also need to think about how to scale the system from cost perspective, as well as some use cases demand lower latency type of things. Sometimes data cannot move through the system, so you can't send data back to the central cloud in some cases. So sometimes this architecture will not work. So the considerations here are, I think I'm losing my train of thought on this.
I'll take it.
There you go.
We work together. And we'll go into a use case later where we talk about something where latency is super important. And so you cannot put the data up in the centralized cloud. You have to leave it down below. And what's important to remember about this is, even though it's centralized control, if one of the units out at the edge goes offline, it still has to be autonomous, at least for a certain amount of time. So here's the fully distributed infrastructure. In this case, there's no centralized control. Each of the units do work in a mesh together, so that they can work independently, but they also work together. So I will do a shout out to Edge Lake, which is a project that is in the AI, I think it's LF Edge, that is doing a distributed database similar to DNS and DHCP, but specifically for AI type workloads or very large workloads. So it's highly distributed, yet it uses blockchain to keep track of everything and keep it secure. So
what you also need to think about with that distributed architecture is the overhead of all the control functions and the edge, or these nodes or sites being autonomous. That means that the control functions will eat more of your hardware. Right. And if you need computational power for your AI, then those control functions will actually make a difference.
Right. So it really depends upon the use case. And again, if it's deeply remote, if it's like a oil drilling platform in the middle of the Gulf of Mexico, that would be, that has enough capability for you to keep it local, and because it's also going to have terrible network connectivity. But there's others where you might want to do, like from a telco cloud, you will have a big pipe back to AWS. So that's just one of the considerations you need to make. So let's take a look at some use cases. Oops, maybe went a little fast there. Okay.
There you go.
Yeah, there we go. Okay, so this is in the white paper, and I go into more detail here, but basically what I did here is I took, and this is just sample use cases, I mean there's hundreds, but I tried to take common use cases and really define the different, the different important components you had to think about. And so for factory automation, for example, how much storage you need is going to vary depending upon the use case. But security is going to really be high. That's actually a significant problem for factories. That they there's secret processes and stuff that they want to keep. And they also, sabotage can be a significant problem. Let me jump down to healthcare, because that's when we go into more detail. Healthcare can, if for imaging stuff like radiology images and that kind of stuff, MRI images, you probably, it's not going to be particularly network latency sensitive. But the example we'll go into in a minute is robotic operations. You need the latency to be, as small as possible, because, you can't really wait for, hey, we're going to wait while the data comes down, during the operation. That's really a bad idea. Robotics and telepresence and those kinds of things really need that very, very low latency. But there's other things like, particularly a lot of the IoT, like remote cameras and things like earthquakes detection and wildlife cameras. Like, who cares? The latency can be a little longer. So there's network latency, the data, how much data is being generated, how much data needs to be put up to someplace else. And then you also have to think about the compute, the storage, and the security. So hopefully this will be a good guide for people to kind of start thinking about the architectures. Whoops. Oh man, I am so bad at this.
You need to just use the arrows.
Okay, just use the arrow keys. So let's, Ildiko will talk about our use cases. We have 3.
Yeah, our time is running out, so I might be kind of quick. So one of the use cases that we have is around the notion of federated learning. So not all the training happens at the same place. And this is an automotive example that talks about traffic prediction and these kind of scenarios for the cars. Obviously, you can't put everything and all the computational responsibilities into one car, because on one hand, when it comes to car manufacturing, what they really want to do is keep the costs as low as humanly, physically, all kinds of ways possible. So cost savings is something that is really important in the automotive industry. And on the other side, you just have limited space and opportunities to install hardware. So one thing that this use case does focus on is keeping data on the cars, doing partial training, and send that up to a remote server where that puts together the different models and gives updates to the cars that are on the road. So the use case keeps all the computation that is necessary for the car and use case to be operational, and does some more computation at a remote location that is not that much time and latency sensitive.
Right, so it's traffic management and traffic awareness. Okay.
And then when it comes to healthcare, there are various aspects of healthcare that you can think about. Smart aging is more about devices around your household, for example, that will help people with their routines and also detecting illnesses and diseases. But it's not something that is necessarily real time like the surgical use case that Beth was mentioning. So this use case is a little bit closer to a traditional edge architecture. However, the raw data does not leave the premises because that is something
Security.
that is personal and very sensitive data. You don't want your health information to be broadcasted all over infrastructure where then anyone can steal that data.
There's regulatory requirements that say
Yes.
can't.
And that too. But then in comparison, when you're doing surgery like laparoscopical surgery and like real-time imaging for surgical reasons, then you have a different type of architecture, which is still layered, but this architecture is still talking about locally where the patient is and the operation happens. You can see the sub 100 millisecond segmentation updates node. So this is one of the very low latency use cases. Again, data does not leave the premises. And architectures like this even focus on power management to make sure that your system is operating on efficient power patterns because the surgical devices are not necessarily the big bulky.
No, they are. So I recently had my gallbladder taken out as part of my broken leg. My gallbladder decided it didn't like it. And I was actually surgically, it was robotic surgery and they did use AI. So it's actually being done. This was at a teaching hospital in Boston that's cutting edge. Now, I didn't personally see the machine because I was asleep at the time, but I was told that, this is top, cutting edge surgery and,
Pretty cool.
So it was very cool.
All right, I think that one.
Yeah, that's mine. So as we've been alluding to, there are significant challenges to running AI at the edge. One of the things is, I think a lot of companies are I know there hasn't been a whole lot of talk about return on investment in business because this is a technical conference, but I think it is something that many companies are really thinking hard about, particularly with AI. Right now, a lot of companies are, spending money on AI, but they're hoping there will be a return on investment, but so far that has not been particularly true, except for specific use cases. But when you add edge into it, that can be a significant challenge. And of course, the fact that at the edge, particularly at the far edge and the extreme edge, the resources are just not there. It's amazing. These phones are, mini computers, and my first computer, didn't do half of, not even 1/10 of what this, my phone does nowadays. But there still are constraints, and that's part of the trick with architecting these edge architectures to support these AI workloads. And of course, I've also mentioned networks. Hey, it's the network, and you have to really think about that data and how much you keep it around, where you keep it, and making it secure, private, etc. And I think you give the future directions. We're doing well.
Yeah, we still have 4 minutes left. So the evolution of AI is unpredictable. If you follow the evolution of AI, there are news articles coming out every day of the different directions and what it can do or theoretically can do. So we are kind of going day to day with this. However, you don't really build architecture that way, especially in a distributed environment. And the things that Beth was mentioning, like the oil rigs in the middle of nowhere, or the antennas again in the middle of nowhere. So it's not something that you will update on a daily basis, just based on how the workload and the technology that's running on top is demanding that particular day. And when it comes to the infrastructure considerations, cost and capabilities will need to be very closely monitored and balanced, because then you end up with a really, really pricey infrastructure, and then if you don't have a return on that investment, then eventually, whether or not it's running something cool AI stuff, it's not gonna make it. And it's not as easy as it looks. You can also follow like the NVIDIA news and all the new GPUs and other hardware bits and pieces that are coming out. Super cool, but they're also not necessarily the cheapest things, especially when they just hit the market. And I mentioned already at the automotive use case, for example, if you can save a penny on a little component, if there's something that will give that saving on that one little component, just because the manufacturing is so huge, it adds up, so they will actually go that route.
And they are not going to put a $20,000 GPU in.
Definitely not. Well, they can, but I'm not gonna buy that car. So
And nobody else would either.
Nobody else would either. So it's not as simple as it looks when you're thinking about very, very large scale. And the good news is that there aren't just proprietary, but also a lot of open source communities have been thinking about AI on literally all levels. If you look into OpenInfra projects and some Linux Foundation projects, like we mentioned, Linux Foundation Edge, Foundation Project Umbrella, you can find a lot of projects who are looking into both of these aspects, both artificial intelligence, machine learning, as well as how you build the infrastructure for all these use cases. And the great thing about these projects is that you can go and just talk about it with others, learn from others' experiences, and find a solution together. Because what we've been learning in the open source ecosystem, the infrastructure is usually not the differentiator. It is something that everybody depends on. So if everybody builds their own, then it's a very wasteful way of going about making use cases come to life. So open source is really highly applicable in the infrastructure space. And then, as we said, it's a highly evolving area. So just keep monitoring where we go in the next 6, 12, 18 months.
So yeah, just to wrap things up, we have one more minute, but I think we have some time for some questions. So I encourage people who are interested in this to join projects. You know, that the Edge Working Group is going to be diving into more into the infrastructure, like the details. So I recommend you read the white paper. It's about 40 pages, so it's pretty detailed.
A lot of use cases, though.
A lot of use cases, and some of the engineers are like, it's not detailed enough. I'm like, okay, whatever. But you know, really think hard about this, and so anyhow, additional resources, the white paper, and you know, here's a couple other. I think we will contribute the slides, so there'll be links. And questions. Q&A. So, any questions?
So, what kind of tool set are available from OpenInfra side for edge computing? Because typically, like whatever organizations developing their own software, they have some kind of tool set on it, right? But at community level, like what are tool sets that we are using?
I mean, when it comes to OpenInfra, we have a handful of projects. OpenStack and StarlingX and product containers are all relevant at the edge. I mean, Beth can mention the Verizon experience product that was like, the box was like this big.
It was the same. Yeah, it was a universal CP, and it was this was before Kata containers came along. So we did it with a very stripped down OpenStack. We then added a product called Application Edge, which was basically a container that sat on top of the infrastructure. And I actually got a patent for it because what we did is we separated the routing and security aspects of it, which were service chained, from the customer application edge piece of it. So that was fully separated from, security, et cetera, so that we could go, when we talk to customer, we'd say, you can put whatever kind of containerized application on it, we will not see it. It has, it's separated from the routing, which made our operations people happy, and it made the customer happy.
One challenge that normally I have observed in the previous summit or meetups or conferences is like different edge devices produce different structural data, right? There is no standardization of data pattern. So when the data is coming and hitting to a centralized location, whatever tools you will use to read those data and make some meaningful reports out of it, sometimes it's going to be very complex because some are generating the YAML formatted data, some are generating JSON, some are completely unstructured. So
yeah, absolutely. That's a significant problem. We did not really talk about that in our use cases because we were assuming that the use case would be sort of a unified use case, like the surgery use case, where the data coming in was all kind of standardized within its own bubble. But it is actually a significant problem. For example, I discovered that even within Verizon, we have a number of networks we support, and the data, the monitoring data that we retrieve in the logs, all different. And there's different definitions of jitter, there's different definitions of latency. I mean, man, it really makes it complicated. And that's just within Verizon. So, every telecom has their own, so that's beyond the scope of this paper, but you're bringing up something that's very significant problem. So, any other questions before we close?
I haven't read the white paper yet, but is there any farming use cases documented on
farming?
Not in this one.
Yeah, we did have it, but we, just in the interest of making the white paper readable rather than a book, we did not happen to include that particular one. But there are several farming use cases, absolutely. I know Verizon does a farming thing with I've seen the demo related to irrigation for making sure that they do moisture testing to make sure to keep the soil the proper moisture, and then they apply irrigation to smart irrigation to save water. So.
Oh, do you happen to have that? Where can I look at it?
That should be on the Verizon website, actually.
Okay, yeah. Because I'm working on something similar.
Yes, well, Verizon does it. I mean, we work with farm associations, and the network is we use. There's a product called Gridwise that uses cell phone or IoT type data to do the.
And now one more question. So now let's say we all understood how this typical edge computing is working and what kind of data they are generating and how it can be consumed. Let's say we would like to contribute something. Where to get started here? Because that point is not very clear to me.
With the Edge Computing Group?
Yeah.
We totally did not include the link to that, did we?
We forgot to include it. When we put it up, we'll
yes, we will update the slide. There's a wiki page that outlines the resources that we have. We have a weekly meeting. That's where we mostly meet on Mondays at 8 a.m. U.S. Pacific time. That is 5 in the afternoon Central European time. And we also have a mailing list where we keep in touch, and that's where we discuss what content we will create next and what topic area we will dive into. Right. So we will update the slides with the details. But if you look for OpenInfra Edge Computing Group, you will find it. So you will stumble on the wiki page and you will find it.
I think it's actually in the white paper. I think the link to the wiki page is in the white paper. Yeah. And as I said, our next project is to dive into the architectures, because we did basically we did a reference model here, and the next step is to bring it down to the next level, down to reference architectures.
So are we expecting some kind of development work on those?
That's the theory. Yes, we have some engineers who are anxious to get into the lab.
So. And if anyone wants to join that effort,
Yeah,
let us know.
absolutely, yeah.
Okay, I think we're significantly over time now, so I will unplug the laptop. But if anyone has any further questions, we are here.
Yeah.
Where can the white paper be found? I'm sorry, I think I was a few seconds too late.
Oh, no, that's okay. We're gonna be posting the slides and it will have a link.
If you go to openinfra.org/projects, the Edge Computing Group is listed